much. I'm Xueqi, and I'm a final year PhD student at Yale, and my advisors are Dr. Warner and Dr. Xueqi Guo. I'm glad here to talk about my thesis. Oh, sorry. So clinically, PET imaging is taken typically as a single frame to measure metabolism activities. However, the tracer dynamics involve some temporal process, and it is better if we can move on to dynamic PET, where we get blood input function, and there's also target tissue activity curves, and by fitting those into kinetic models, we are able to get physiological parameters measuring tracer uptake. And we can see in parametric images, we get clearer boundary of the tumor and also higher contrast ratio. So static PET may provide us with bias, and if we go to dynamic PET, there's going to be fully quantitative parametric imaging. However, there's one challenge in dynamic PET that is subject to motion. You can see that misalignment not only appear in those dynamic frames, but also in the following parametric images. We can certainly implement conventional non-rigid registration to correct this, and we can see the alignment in dynamic frames and parametric images are improved both. However, it can take about 10 hours even for one single pair, which is impractical. So we move forward to deep learning methods with fast inference. This single pair unit is very popular, but keep in mind that tracer kinetics is a temporal process that may involve multiple pair analysis. So my first part of the work is extending this 3D unit on temporal dimension and also adding convolutional LSTM as a bottleneck for high-dimensional analysis. So with spatial temporal analysis, the network is able to address tracer distribution change, and we can see the motion correction results are improved. However, if we step forward, since motion may introduce bias or error in parametric fitting, then if we can directly address this problem in the motion correction network training, the performance of the network is expected to improve. So the second part of my contribution is adding this PELAC model fitting block in addition to the motion estimation network, and also to optimize the parametric fitting loss directly. In this way, the network is able to give us even more improved motion correction results and the reduced parametric fitting error. However, if we come to other tracers with more rapid kinetics, most of the motion correction methods may cause failure. That is because the looking of those early frames and late frames are very significantly different from each other. So alternatively, we think of developing an early to late mapping model to convert those early frames to the frames with similar looking to the late frames. And by applying motion correction on those converted frames, we'll be able to achieve successful results. And this network is achieved by a generative adversarial network, but both informed temporally and anatomically. So that concludes my wonderful year spent at Yale, and I would like to acknowledge my advisors and classmates. Thank you very much for your attention.